I left off on example 3. Okay. So what's the problem with this? Square root. Okay, so what they did here was they factored out an x squared from the top and an x from the bottom, so that the square root would go away on that one term. So I'll try that. X squared 3 over x cubed. Or wait. Or no, this be x. Or 3, I mean. Plus 6 over x. No. 6 over x squared. Yeah. Then we got x 5 over x minus 2x over x squared. And then these are split up. This becomes an x times the square root of 3 plus 6 over x squared. Over x times 5 over x minus 2x over x squared. And we want to split these up or something. What did I do before? Oh yeah, if it's you plug it into the fraction and it approaches 0 and all that. What did I do though? Oh wait, this is 2x already over here. Never mind. This is where we need to be really careful with the square root in this problem. Don't forget that the square root of x squared equals the absolute value of x. Square roots are always positive, and so we need the absolute value bars on the x to make sure that we will get a positive answer. This is not something that most people ever remember seeing in an algebra class, and in fact it's not always given in an algebra class. However, at this point it becomes absolutely vital that we know and use this fact. Using this fact, the limit becomes... yeah. Okay. now we can't just cancel the x's. We'll need to get rid of the absolute value bars. To do this, let's recall the definition of absolute value. In this case, we're going out to plus infinity, so we can safely assume that the x will be positive. So we just drop the absolute value bars, and the limit is... Okay, I see what they do. So it's going to split off from here. Let's now take a look at the second limit, the one with the negative infinity. In this case, we need to pay close attention to the limit that we are using. The initial work will be the same until we reach the following step. In this limit, we are going to minus infinity, so we can assume that the x is negative. So in order to drop the absolute value bars, in this case, we will need to tack on a minus sign as well. So it's just okay. So as we saw in the last two examples, sometimes the infinity and the limit will affect the answer and other times it won't. Note as well that it doesn't always just change the sign of the number. It can on occasion completely change the value. We'll see an example or two of this in the next section. Before moving on to a couple more examples, let's revisit the idea of asymptotes that we saw in the previous section. Just as we can have vertical asymptotes defined in terms of limits, we can also have horizontal asymptotes defined in terms of limits. Definition: the function f of x will have a horizontal asymptote at y equals L if either of the following are true. If the limit of f of x is x approaches positive infinity equals L, and the limit of f of x is x approaches negative infinity equals L. Okay. We're not going to be doing much with asymptotes here, but it's an easy fact to give, and we use the previous example to illustrate all the asymptote ideas we've seen in both this section and the previous section. The function in the last example will have two horizontal asymptotes. It will also have a vertical asymptote. Here's a graph of the function showing these. Let's work on a couple of examples involving rational expressions. Probably the following limits. Okay. Okay, so we're going to want to factor out z squared from the top. Right, no, z to the power of 6. And then z 3 to the power of 6 from the bottom. Okay, these cancel out. Oh, this goes to 0. Get 1 over 0. So it's an asymptote. You can't cancel out. Sign analysis, I guess. But how would you do that for this? Let me see how this works again.
But now it's here. Can I plug this into points of your life? Nice, right? Right? You don't. If you pick the problem, because as soon as I cross out this x plus 4, now when I, but before you factor correctly. All right, thank God. Good. At least we factored it correctly. Do you see anything that simplifies? Wait, not both x minus 5s? One thing. So we go here and here, yes? And what we get out of this is an important example for you to see. You get x plus 2, x is still approaching 5, x minus 5. Try to plug in the 5, what are you going to get? 0. You're going to 7 over 0. Is that still a problem? Yes. Oh man, so wait a second. What do you do if you still have a domain issue on this thing? I've now given you 2 cases. I've given you cases where the problem, the domain issue is a hole. Do you see that? It's a hole, and you can get rid of a hole. It's a removable discontinuity, and you can find the limit of that. It's very easy. You factor it, and then you evaluate. Now, I've also given you another case where not only that is, well, this is where you're going to use what's called a sign analysis test. Listen, you really do have to comprehend that if you can get a 0 over 0, like you did over here, you're going to be able to at least factor it and simplify something, right? Sometimes, as I've shown you, it will get rid of the problem area, and you can just substitute in a number and be just fine. That happened here, and that happened here. Now, do you have to be okay with that one? Now, other times, sure, we got 0 over 0. We factored it. We got rid of what looked like a problem area, and it was. That's like a hole. However, can you get rid of this x minus 5 in any way whatsoever? If you can't, what was that called again? It's asymptote. What you have to do, sign analysis test. Here's what you do with a sign analysis test. You put the numbers that will make the numerator and the denominator equal to 0.
Okay, that's what I thought. Wait. No. Hmm. Okay, I'm stuck. What do you do? Let's do the first limit. And in this case, it looks like we will factor a z cubed out of both the numerator and the denominator. Oh wait, you don't factor the biggest from the top and bottom? Okay, wait, let me try that. Okay, these cancel out. Zero plus z cubed over 0 minus 5. Z cubed over 5 negative. So, yeah. The final limit is negative because we have a quotient of positive infinity and a negative infinity. Now let's take a look at the second limit. Note that the only difference in work is the final evaluation step, so we'll pick up the work there. In this case, the z cubed in the numerator gives negative infinity in the limit, since we are going out to minus infinity and the power is odd. Then the answer is positive since we have a quotient of two negative numbers. Evaluate the following limit. Just negative infinity, huh? Alright, so first factor out common power. these cancel. 1 minus 0 minus 0. I guess if you plus 0 technically, but it doesn't matter at all. Actually, I don't even know what it doesn't matter. Either way. It might not even matter because these just approach 0 anyway. Two t squared plus 3t. One over 2t squared plus 3t. So the bottom is approaching negative infinity. So it should be 0, right? Should this be approaching 0? Yep. But what did I do wrong at the top? What is that? P to the power of 4. Why though? Wait, but they didn't do that in this one. They didn't factor out a z to the power of 6. Is it whatever is biggest in the denominator? What we'll do here is factor the largest power of x out of the whole polynomial. Alright, I don't really understand that. In this case, using fact 1, we can see the numerator is 0 since the denominator is also not 0 in the fraction, and hence the limit will be 0. In this section, we concentrated on limits at infinity with functions that only involve polynomials and or rational expression involving polynomials. There are many more types of functions that we could use here. That is the subject of the next section. To see a precise and mathematical definition of this kind of limit, see the definition of a limit section at the end of this chapter. In the previous section, we looked at limits at infinity of polynomials and irrational expressions involving polynomials. In this section, we want to look at some of the other types of functions that often show up in limits at infinity. The functions we'll be looking at here are exponentials, natural logarithms, and inverse tangents. Let's start by taking a look at some very basic limits involving exponential functions. E. Well, if you just graph E, the limit of e to the power of x as x approaches infinity, it's obviously going to be infinity. So if you just plug in infinity, it's infinity. So. Of e to the power of x, x approaches negative infinity. We'll see for this, this is gonna approach 0. I don't know if you can mathematically prove how to do this, because e is kind of a weird number. As x approaches infinity, I'm guessing it's gonna be flipped. Okay. So if you're going infinity, or wait, I put the negative in the wrong place. The negative is on the x. Wait, what's that do to it? Okay, it flips it that way. So as x approaches infinity, it's gonna approach 0. What's the last one? Negative x. As x approaches negative infinity, it's gonna be infinity. Infinity, 0, 0, infinity. These are really just restatements of the facts given in the basic exponential function of the review, so we'll leave it to you to go back and verify. Okay, well, I verified it myself. So. The main point of this example was to point out that if the exponent of an exponential goes to infinity and the limit, then the exponential function will also go to infinity. Wait. The main point of this example is to point out that if the exponent of an exponential goes to infinity and the limit, then the exponential function will also go to infinity at the limit. Likewise, if the exponent goes to minus infinity and the limit, the exponential will go to 0 and the limit. Note as well that in the last section, the value of the limit did not depend on whether we went to plus or minus infinity. We've already seen in the above example that changing the sign of the infinity can change the answer, so do not get locked into any assumptions that you may have made from the work in the last section. Here's a quick set of examples to illustrate these ideas. Okay. Alright, first thing I do is factor out x squared, maybe? Approach 0. It would be e to the power of negative infinity, so 0. In this part, we need to note, using fact 2 above, is that in the limit, the exponent of the exponential does the following. So the exponent goes to minus infinity in the limit, and so the exponential must go to 0 in the limit using the ideas from the previous set of examples. So here is, okay. limit of e to the power of t to the power of 4 minus 5t squared plus 1 as x approaches negative infinity. Okay, so we got this. Alright. It's gonna end up being 1. So negative infinity. So it's gonna be 0 again. Or not. How does this equal positive infinity? Why does it do this? Go to math. Oh, because it's a negative that you're plugging in. It's a positive. It's an even exponent. Okay. Yeah, I see. And the limit of e to the power of infinity would be infinity. What is this, symbol here? 0? What? From the right. Okay. Let's work some more complicated examples involving exponentials. In the following set of examples, it won't be that the exponents are more complicated, but instead that there will be more than one exponential function to deal with. What the?
Выйди нахуй с комнаты отсюда, долбоёб. Да я тебе сейчас въебало выеду. Ебать. Я на парня, чё, я разберусь нахуй.
Okay, wait. So this would be positive infinity. Okay, no, actually, what do you do here? Like, this is weird. You got positive, negative, positive. It's a negative here. It's e approaches of negative infinity. What did we say that was? Zero. So that should be 0, right? Yeah. Then minus 0. First 3 are our problem, however. They present us with another intermediate form. When dealing with polynomials, we factored out the term with the largest exponent in it. Let's do the same thing here. However, we have to deal with both positive and negative exponents and ask just what do we mean by the largest exponent. When dealing with these, here we look at the terms that are causing the problems and ask what is the largest exponent in those terms. So since only the first 3 terms are causing us problems, we'll only look at those. Since 10x is the largest of the 3 exponents, there we'll factor out and e10x out of the whole thing, just as with polynomials we do. Okay. Jeez, man. I'm not factoring all that. I'll write this down, but like, jeez. Wait, I don't want to write down the original. Okay, and the other one for negative infinity. What'd you get? Zero. 0, 0. Zero. Infinity. Minus infinity. Yeah. So if you did all this again, factoring out the 10x, well, you just get negative infinity again, wouldn't you? Or not again, but this time you get negative infinity. Okay, so you get the intermediate form again. So you factor them out. Said we're going to use the largest to refer to the exponent that is farther away from 0. Why? Why would you do that? It's a negative? Really? So when dealing with sums and or differences of exponential functions, we look for the exponential of the largest exponent. And remember here that largest means the exponent farthest from 0. Also remember that if we're looking for a limit at plus infinity, only the exponentials with positive exponents are going to cause problems. So those are the only terms that we're looking at for the largest exponent. Oh, is that how it works? Looking at a limit at minus infinity, then only exponentials with negative exponents are going to cause problems. So those are looked at in determining the largest exponent. Okay. Again, it's exponentials with positive exponents. And if we're looking at a limit at minus infinity, we only look at exponentials with negative exponents. Okay, wait. So for this, you're finding a positive infinity. You're going to factor out the 6e to the power of 4x, or just the e to the power of 4x. From the top and bottom. I think I'm not going to write example 4 down. I'm just going to walk through it real quick. I do just want to move on to derivatives, honestly, because this section isn't in the Professor Leonard video till later on with the limits at infinity. And it's like, feels kind of pointless right now. But I'll just read it. Basic concepts involved in working this problem is the same. Okay, so they do factor out the e to the power of 4x. Cancel it out. They plug in the infinity. 6 minus 0. 8 minus 0 plus 0. And they simplify, the limit is 3/4. Down here, you do the exact same thing, except you're plugging in a negative infinity, so you're gonna get 6. Well, let's pull this up. Oh, they don't? Wait. Again, remember to only look at the denominator. Do not use the exponential form from the numerator, even though that one is larger, the exponential in the denominator. You always look at the denominator when determining what term to factor out, regardless of what is going on in the numerator. Oh, that's the problem I had earlier. Okay. But still, why do you factor out a negative x? In this case, we're going to minus infinity, and the limits will look at the exponentials in the denominator with negative exponents. Really? Okay, so they factor out the negative. Let's see, for this one, they're going to negative, so they look at the denominator, factor out the negative that's farthest away from 0. Cancel that out, plug in negative infinity. 0 minus 0, 0 minus 5. It's 0 over negative 5, and it's 0. Okay. Now let's take a quick look at some basic limits involving logarithms. Zero from the right. Okay, well, let me pull up Desmos again, graph that. Yeah, so if x is approaching 0 from the right, you're going to negative infinity. And as x approaches infinity, you're going to infinity. Note that we had to do a right-handed limit for the first one since we can't plug in negative x's into a logarithm. Since the normal limit won't exist, so you must look at x's from both sides at the point. Question x's to the left of 0 or negative. Goes to 0 from the right, always positive. The log goes to negative infinity. We can't look at a logarithm as x approaches minus infinity. We can't plug in negative numbers. Alright, so this is kind of the same as the e to the power of problem things. So first I'd find the limit of 7x cubed minus x squared plus 1. Factor out an x cubed. Approaches 0, approaches 0. 7, positive infinity. So this would be a positive infinity. And that'd be positive infinity, okay. For this one, it's gonna approach 0, and it's doesn't exist. No. Oh, you just assume it's going to 0 from the right. The denominator will always be positive. Quotient. Oh, okay. That makes sense. Alright, inverse tangents. A should be infinity. Or no. Pi over 2, yeah. These horizontal asymptotes. Negative would be negative pi over 2. The limit, okay, well, I'm not even gonna write this all out. Factor out an x cubed, 1 minus 5 over x squared plus 6 over x cubed, positive infinity. Same thing, pi over 2. For this one, 0 from the left. What's the limit of 1 over x is as x approaches 0 from the left? negative infinity. Negative infinity then? Or wait, no, negative pi over 2. Okay. Alright, well, it's continuous at x equals negative 2. Or no, it's not. Because there's a it's a jump, so it's not continuous there. It is continuous at x equals 0. Not continuous at x equals 3 because there's another jump. Yeah, negative 2 doesn't exist. Jump discontinuity. 0. Function's continuous. Yeah, removable discontinuity. Yeah. Determine that the function below is not continuous. Okay, set it equal to 0. Or really, just set the denominator equal to 0. So we're really looking for asymptotes and poles. Okay, so there's going to be an asymptote at t equals 5 and t equals negative 3. So that's where it's not continuous. Sine. It's going to be 1, right? Yep. Since we know exponentials are continuous everywhere, we can use the fact above. Okay. Okay, I'm skimming through this because I really just want to move on. Precise mathematical definition of 3 kinds of limits we looked at in this chapter. I'm not too interested in this section. Too boring, unfortunately. Let's just hop right into derivatives. Straight up.
Well, welcome to the 2.1 is called the derivative.
This is what we want to see.
An ominous sounding title. This thing should look familiar. Geez, I hope that looks familiar. Does that look familiar to you? Yeah. Good, because if it doesn't, you haven't been here the last 45 minutes. Okay, that looks familiar. We've used this for a few things. We've used this to find the instantaneous rate of change. We've used it to find instantaneous velocity. We've used it to find the slope of a curve at a point. We've used it to find the equation of a tangent line by finding the slope of that curve and then making an equation out of it. So this is, I'll just call it this, because it's what all those things mean. This is the slope of a curve at a point. Slope of a curve at a point. This thing, which I've already told you, stands for the slope, right? This thing says as you approach one single point. So this is the slope of a curve, that's f, at a single point. You got the idea? What this idea represents is something called the derivative. So what is a derivative? There you go, my job is done. I've already taught you that. I've taught you a derivative. I just didn't tell you it was a derivative. This thing is a derivative. This idea is a derivative. Well, here's the thing about it, all right? You're going to be taking lots of derivatives, and like I've told you before, people in calculus, they get so involved in doing the computation, they forget what you're actually doing. What are you doing when you're finding a derivative? What are you finding? That's what you're doing. What are you doing, everybody? You're finding the That's what a derivative represents. This thing is the slope of a curve at a point. That's the derivative function. It's telling you how to find the slope of a curve at a point. So when we're taking derivatives, that's all we're doing. And there's a special notation for it. The derivative looks like this. That's the function, right, that we're talking about here. How you say go from a function to a derivative, it's very easy. I'll give you some more notation later on. But you go, okay, this is a function. If that's a function, that's a derivative. Put a little apostrophe thing up at the, it's not a 1, it's not a 1. It's like that. Some people have a little dash. It's not a 1. The derivative of a function, that's what this says, the derivative of a function, or the slope of this function at any point that I want, is the limit as h approaches 0 of the difference quotient we've already talked about. And you know what? In general, we're not going to have a specific point. So I'm going to erase the x sub 0. I'm going to say we're not going to do this at a specific point anymore. Maybe we'll do that later. What we care about is the derivative function. We want the equation, like we did here. We want the equation for the slope of a curve at a point. You with me on that? We're going to stop doing this for a specific point. We might plug in some afterwards, but I want the function itself, because what you found out in the last example over here was, if I told you to plug in more than one point, that gets pretty cumbersome and tedious, right? You have to do it for every single point. That sucks. Now, are you 2 points? That's what we're saying. The rate of change, of course, we need to make it a little bit more mathy than that. Here's the mathy part of it. This is going to go very quick because you can see it's exactly the same thing that we've just been doing, okay? Here's what's the instantaneous speed? Well, you just take of t plus h. Well, sure, we have t plus h over here. If we do this, they're gone. You have 500 minus 400 minus 100. You see that? Good. All right. We're going to continue talking about this problem. Now, what we're doing is we're trying to find not the average velocity of something, which is, we found out last time, simply the slope between 2 points. We don't want to find the average displacement over time. We want to now find the instantaneous velocity. So how fast is an object moving at a specific point in time, an instant, like at that one moment? It could change before, it could change after, but right then, not an average, but an instant. Like, I think I gave this example. If you're driving down to LA, you go from here to LA, let's say it's about 300 miles, right? If you make it in 5 hours, how fast were you going? See, a lot of you are saying 60 right now, right? Because you're doing 300 miles divided by 5 hours would give you 60 miles per hour, true? That would be your computation ahead. However, what you just did was an average velocity, an average speed, as a matter of fact. Velocity if you went to the direction. But that's an average, right? The overall distance divided by the overall time gives you how fast you're going on average. Now, realistically,
I didn't watch this video. I don't know, it said... It's acting like I watched the whole thing. That's why I was confused.
now, are you ready to learn how we can take limits and use them? First, I've already kind of shown you a basic idea of how to do this, how to find the slope of a curve at a point. Would you like to learn how to do it for real, using limits? Are you sure? So the answer is yes, otherwise you get to leave the class because this is where calculus is going now. So would you like to learn it?
Yeah.
Otherwise you're not going to learn calculus.
What was I watching here? I was still watching continuity. Wait, did I started this? Yeah. Or wait, no. It's probably the end of this video, the continuity one. Yeah, I never watched this. Dude, that's why I was like, what is he doing? Yeah, okay, choose. We'll skip the video. Never mind, not on derivatives yet. But it seems like this leads into derivatives anyway, so. This is what happens when you don't do this for like a week.
Now, are you ready to learn how we can take limits and use them? First, I've already kind of shown you a basic idea of how
I'll
to
watch
do
like
this,
10
how to
minutes
find
of this.
the slope of a curve at a point. Would you like to learn how to do it for real, using limits? Are you sure? The answer is yes, otherwise you get to leave the class because this is where calculus is going now. So, would you like to learn it?
Yeah.
Otherwise you're not going to learn calculus. You're going to learn, well, just basic algebra and limits. That's all we've done so far. Ready to learn calculus? You should be jumpy. Yeah. You can watch that again on YouTube. Maybe you don't want to.
Too scared.
Well, you've never seen a grown man get excited about calculus before? Come on, people.
No.
This is awesome. Well, first time for everything. 1.5. We're going to talk about tangent lines. We're going to apply them to rates of change, and you're going to see that we can take our idea of limits and turn it into a tangent line, and turn it into a rate of change. It's going to be kind of an interesting idea. I need you to follow through. This is like a kind of a, not really a proof, kind of a semi-proof. We're going to be creating the slope of a curve at a point. I'll give you a definition for how we say the slope of a curve at a point in the next section. For right now, this is what we're doing though. In the first part of calculus, what we want to do is find the tangent to a curve, right? In order to find the tangent of a curve, you need a slope and a point. The point's going to be given. What we want to be able to do is find the slope of a curve at a point. That's our whole idea. So that's why we'll be talking about tangent lines, and then rates of change follows directly from that.
Nice.
So we're going to use limits to find the slope of a tangent line to a curve at a point. I'm going to actually write that down so you understand what we're doing. Again, in calculus, a lot of people get halfway through and they forget what it is they're actually doing. They just get caught up in the formulas and doing the math, and they're not really focusing on what they're doing. What we're doing anytime we do this process, we're finding the slope of a curve at a point, or the slope of a tangent line to a curve at a point. So we're using limits. To find the slope of a tangent line to a curve at a point. Let me say of the tangent line. And that folks, is the first idea. The first problem in calculus.
Alright, using limits to find the slope of a tangent line to a curve at a point. Which we already did, but we did it less good.
We're going to create it from scratch. So I want you to understand where this is coming from. Some of you will have seen part of this formula before in your pre-calculus class. Some of you might have seen it in your intermediate algebra class. It's going to look familiar. You're like, wait a second, that's why we did that. Because at the time you're like, what the heck is this? Why are we using it? You're going to see why you're using that. So we're going to invent this formula together. That way you see where it's coming from. Would you like to do that?
Yeah.
Rather than I just give it, I hated that. I want you to see where it's coming from and understand it. Part of math isn't just doing the math, it's understanding it. That way you have a better understanding later on. So here's our creation. Our idea again, I'm going to draw my same curve I did before. We want to find the slope of this curve at some point, and I'm going to call it P again. What was the other point that I used?
Q.
Yeah. Now, our idea was that we're going to take Q and have it really, really close to P, right? That was the idea of a limit, really, really close without touching it. That's the idea here. Now, what we're going to do is define this a little bit differently than I did before. You see, we are going to find the slope of the secant line. That's the line that connects those 2 points. But here's how I'd like to do it. The first thing I want to do is say, okay, P is some point, let's call it x sub 0. Just my point, and it's fixed. It's my actual solid point, x sub 0. You okay with this so far? Let's see. Is that straighter or less straight? Is that horrible? That's better. It looks better. Am I wearing different size shoes or something? That's horrible. Okay, x sub 0. And this point, how far is that? How far is that? Well, you can't say, oh, it's 7. Well, there's no actual value, right? We're doing this in general. We don't want to use a different variable. We want it based on this one. But here's how I'm going to do it. I want to say, okay, this is x sub 0 plus a little teeny bit. Are you with me on that? Plus a little teeny bit. Here's why I want to do the plus a little teeny bit. Because I want to introduce the limits to you right now. Because if I do plus a little teeny bit, and I take that little teeny bit and I let it go to 0, think about this for a second. If I let the little teeny bit go to 0, that squeezes point Q all the way over to point P. Do you see it? If I let it approach 0. So here's how we're going to define it. We're not going to call it anything else. We're going to say this is x sub 0 plus a little bit. And h is that little bit. Now keep in mind, this is not to scale, okay? What we actually are doing is P and Q are going to become so close to each other that it's no difference. Okay, are you ready to find out this, the height? Let's figure out those 2 points. How high is point P? Can you tell me that? Yeah, let's assume this function is f. Then that would be f of what now? No, not P. Not P. F sub 0, because that's our x-coordinate for P. So far, so good? How about the top point, our Q? Sure, we know to find out the height of our function, we just plug in the x-coordinates. That's how functions work. So we now have this thing. What we want to do, remember our idea is this. Never forget the idea. We want to find the slope of the tangent line to a curve at a point. Our point is point P right now. Are you with me on that? We want to find the slope of this curve at point P, basically, is what we're doing. So this is our point. What we're going to do with that, though, is, well, we need how many points to make a line?
2.
How many points to find the slope?
2.
You don't have to whisper it. How many? 2. Yes, you're all right. Yeah, you need 2. Yeah, you need 2 points. Say proudly, 2 points. Yeah, you need 2, so we have these 2 points. But our idea is, let's just take point Q and put it a little bit past point P. You follow me on that? Because ultimately, we're going to take this distance and make it 0, or make it approach 0, not equal 0, because then we wouldn't have 2 points anymore. We're going to make it approach 0. That means get really, really close, and that's the idea of a limit. Do you see why we had to have limits before we could do this idea? Okay. Well, let's keep going. Let's find some slope out. Why don't you tell me what is slope? Oh, very good. Okay, rise over run. Give me another way you would do it. Very good. Okay, change in, you have it backwards, but change in, there you go. The change in y over the change in x. Let's find out the change in y and the change in x. Can you tell me, our change in y goes from point P to point Q. How far is that? Or in other words, how could I figure it out? Okay, let me give you some, okay, hang on. This is 10, this is 3. How far is it between them? Very good. How'd you do it? Subtracted 3 minus 10 or 10 minus 3? Hopefully 10 minus 3. The big one minus the small one, right? So how we do this is we go, okay, well, this is not 10 minus 3. It is, do it again for me. Very good. This value, and you could use parentheses if you want, but it's not necessary here. X sub 0 plus h minus x sub 0 will give you the distance between it. This is all of x sub 0 plus h minus x sub 0 will give you the distance between those two x values. Now, if you're still okay with that, it's kind of a big one. Okay, do the math. What's this going to be? That is h. That's just h. Well, that should make sense. I mean, how far apart is x sub 0 from x sub 0 plus h?
This makes a lot of sense.
It's just h, right? It's just a little bit. If h was 2, it would be 2 apart. If h is 0.00001, well, then they're 0.00001 apart. It's just h. Just h. Now, let's go ahead. Let's also find the rise. How much is the rise?
F of H.
No, not f of h. Not f of h. If this was 10 and this was 3, the distance between them would be 7. True. Now, how did you do that? Subtractive, so subtractive. You know, I'm going to do this over here so you can see it a little bit better. This is f of x sub 0 plus h, right? This is f of x sub 0. So write that out. Don't do the math in your head, just because you're making a mistake on that right now, some of you. I want you to write out exactly what it is. Write out exactly what I want you to. What is it? F of x sub 0 plus h. That's the first value. What am I subtracting from that? By a show of hands, how many people feel, okay, I'm getting not only the h, but now getting this rise? Feel all right with that? Yes, no? Okay. Now, Where did people go wrong and give me f of h? Can you subtract x sub 0 minus x sub 0? The answer is no, you can't do that. That's impossible. You cannot combine those two things. So this is the function at this point. This is the function at this point. Those are two distinct points, right? You can't subtract them and give me the function at the difference between them. That's completely the wrong way to go. Right, this would be the height at x sub 0, that's that one. This is the height of x sub 0 plus h, that's that one. If you find f of h is like way down here, right? H is just a little bitty point. A little bitty, f of h is right here. That's going to be very different than anything between those, anything having to do with that. You can't just subtract a function minus a function and subtract the input values like that. You can't do that. Okay, so there's no way we can actually simplify that part of it. Do you agree? Nothing we can do with that. However, can you come up with the formula for a slope right now? So we have slope is rise over run, delta y over delta x. What is our delta y in this case?
F of x plus 0 plus h minus f of x sub 0.
Yeah, it's hard to say, isn't it? F of x, that's why you get a master's degree, you can say all this. They teach you all, no, that's not what they teach you. F of x sub 0 plus h, sure, minus f of x plus 0, f of x sub 0. So this right here is our delta y. This right here is our delta x. So right now, we actually have the formula for slope. But I need you to understand where that comes from. Are you okay that this is in fact the rise and this is in fact the run? Are you okay with that? Do you see where it's coming from on your graph? Does that look familiar? Have you ever heard of the difference quotient before? That's the difference quotient. You might have had that in your pre-calculus class. I'm sure you had that in your pre-calculus class. You did a lot of work with that, right? Why? Because we're now going to extrapolate from that and get the slope of a curve at a point. Cool? Cool. Now here's the deal. What we've done right now is we have the slope, sure, but is it the slope of a tangent or the slope of a secant?
Secant.
Okay, secant, yes, secant. We have the slope between these two actual fixed points right now, yes? What we want to do is just what we did like the first couple days of this calculus course, not the review, but the calculus part of this. We want to let point Q get really close to point P, and I've said it before in here, but how are we going to do that? We can't change x sub 0, that's fixed, okay? What are we going to do to let this get close to that? What happens?
Move it really close.
Does h get bigger? Does h get smaller? How much smaller? Infinitely smaller. So infinitely close to, in other words, that means let h approach 0. So what we're going to do is we're going to make, so this is a secant right now. In order to get the tangent, we're going to make point Q get close to point P. Make Q get really close to point B, point P. How, you might ask? Well, we're going to take that h, we're going to make it close to 0. That says the distance between them is very, very, very small. Well, tell me something. I can't just say, oh yeah, I'm going to make h 0. I have to introduce something that we've had in this class before. What allows you to take a value, a variable, and move it close to a number? What was that?
Limit.
It's called the limit. So here's how we make the jump from a secant, which is what this is. That's just the slope of, you could do this with any line. It's going to find the slope for any point. That's what it is. If you know the distance points, that's what that is saying. Okay, that is the slope formula. It's just a different way to write it. How we make the jump from this secant to the tangent that I'm going to write over here is we're going to let h approach 0. That involves the limit. That's why we had to have limits. So this one's the secant. We want the slope of the tangent line. The slope of the tangent line is going to look almost identical. It's going to have the f of x sub 0 plus h minus f of x sub 0 all over h. Only now, what do we want the h to do? So we need a limit as a approach 0. I could have just given you that, right, and said that's the slope of the tangent line. But do you see what's happening here? Do you see how this is the slope of any 2 points that I want? Okay, this is the slope, and this is the distance between those 2 points. And what this says is I'm making that distance get really close to 0. Can it ever equal 0? No. No. In fact, if you plug in 0, what happens?
Undefined.
You get something undefined. Why does that happen? It says, well, if you only have 1 point, i.e. you let it go to 0 and get there, you only have 1 point, right? Can you find the slope of 1 point? That doesn't make any sense. So you can't let it get to 0. That's why we had to use the limit and say we're approaching 0, where the distance between those numbers doesn't make that much of a significant difference, but there is a small, small difference. That's why we had to have that limit idea. Would you like to see an example about how to actually use this? For sure. I would hope so. It's kind of interesting, right? We just kind of proved that you can find a slope of a curve at a point. Isn't that? That's kind of neat. I know we've done it one time before, but it took a whole lot of work. Now we're going to minimize our work, I hope. So let's try this. We've done this example. We did it the long way. Now we're going to have a nice, easier way to do this. So find the equation. I'm sorry, of the tangent line. To y equals x squared at the point. Right now, I'm going to give you an actual point. That's how I've defined our function. X sub 0 is the actual value. It's a fixed point of x. Okay, it says you have an x value of this number. In the future, I'm not going to give you that. We're going to be able to find the slope at any point, and that's even more cool, even more cooler at 1, 1. But the first thing we got to do, we got to figure out what all this stuff is. And where you start is you got to define your function. So in our case, what is f of x? What are we going to treat as f of x? X squared. Good. That's important for you to know that because we're going to be referring back to x squared a lot right now. Also, you need to identify what is x sub 0 for this specific case. In our case, what is the x coordinate, that's our x, of the fixed point? 1. So x sub 0 in our case is 1. It says you're starting at the point 1. Are you guys all right with that? Not because this is the 1, that would be the output. That would be f of x sub 0, or that's what we get when we plug in 1. But the x sub 0 is 1. That's the x coordinate of our fixed point. You okay with this so far? Now I'm going to encourage you to do a couple things before you just blindly plug this stuff in. I want you to find the f of x sub 0 plus h and the f of x sub 0 independently. So in our case, we want to find f of x sub 0 plus h. Tell me, what was x sub 0 again? 1. So we want to find x sub 0 plus h, but x sub 0 is 1. I want to find f of what?
1 plus
1 plus h. Make the jump from x sub 0 to what your value actually is for x sub 0. Do you follow that one? So this is 1 plus h. Give me a head nod if you see where the 1 is coming from. Good, all right. Also, we want f of x sub 0. F of x sub 0 is really f of what?
1.
Very good.
So 1.
So, short little recap. We identify our function, we identify the point. Those two things are there. This right here is your formula to find the slope of a tangent line. That's it. All you've got to be able to do, h is not going to change. You just need to find this thing and this thing accurately, plug it in, and find your limit. This is going to incorporate a lot of things we've done in this class already. So f of x sub 0 plus h, that is f of 1 plus h. F of x sub 0, that is f of 1, because x sub 0 is 1. You with me? Let's start on the easy part. What's f of 1 say to do? Plug in 1. Yeah, plug in 1. Where are we going to plug in 1? Yeah, so plug in 1. How much is that going to give you? 1 squared is 1. Sure. In fact, it should give it to you right here, right? Because that is the output. I mean, it should give it to you. If it gives you the whole point, that's even easier. If it says as at x equals a number, well then yes, you actually have to plug it in on your own. Now, how about f of 1 plus h? What do you do with that?
Turn it into a polynomial.
Turn it into, what do you mean?
Plug
Plug it into f. You know what this meant? This meant plug in 1, right? You know what this means? Plug in 1 plus h. I always told my students, I said, look it, this thing is non-separable. You can't do this. Well, please watch the board. Common mistake all the time when you first learn this, especially compositions, if you struggle with that. People go, okay, this is f. Okay, I want f of x. I want to do 1 plus h, so they'll give me this. Let's do 1 squared plus h, because that's f of 1 plus h. Do you see the mistake? This isn't 1 f of 1 plus h. That'd be written like this. That's what that would be. That is that. Okay? This isn't f of 1 plus h. It's f of 1 plus h. Okay? You can't separate it. It's like one thing for you, right? Whatever I have in there, that's what you're plugging in. You don't do f of 1 plus h. You do f of 1 plus h. Like it's one word. Do you get it? You cannot separate it. So in our case, we're not doing 1 plus h. No, 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 no. We're doing f of 1 plus h. So what's that going to be? 1 plus h squared. Do you see how to get from here to here? Are you sure? Not f of 1 plus, oh please, please don't do that. It's never going to work for you if you do that. Never. Oh my gosh, that would be horrible. Well, now all we've got to do is take these quantities that you just figured out, substitute them into my formula for my slope of the tangent line, and we'll be done. More or less.
Is that more or less it's scary?
Yeah, no, it's less. It's stuff you've already done. Very easy. So instead of x sub 0, f of x sub 0 plus h, I've already figured that out. That was 1 plus h squared. That's what I'm going to put first. Minus, instead of f of x sub 0, what did I work that out to? That's why I have you do off the side, right? You just break it down piece by piece. That's okay. F of 1 plus h was 1 plus h squared. F of 1 is 1. All over how much? Oh, don't forget that h. Don't forget that h. Okay. And now here's where you try to plug in the number, because this is a limit now, right? This is just a limit, which we've already conquered those sections. You plug in 0. Can you plug in 0? You get, 0 over 0, right? That's a problem, don't you? Or you get something over 0. Looks like 0 over 0 to me. So, we need to do something else then. Why don't we figure out what this is? So let's go ahead and distribute that. Combine some like terms.
Okay, well this is a whole
and see what happens. Don't forget to write the limit. Let's see, that's 1 plus 2h plus h squared minus 1 over h. Did you get the same thing when you distributed as well? What happens here? The ones are gone. Okay, I like that. That's great. So that is the limit as h goes to 0 of 2h plus h squared over h. Oh man, if I plug in 0 right now, it's still going to 0 over 0. What's another thing that I might be able to do? Do you remember whenever we had a 0 over 0, typically what you do is you factor, right? And that sometimes, most of the time, will work your problem out for you. That's what we're doing here. Now, is it a problem for our domain that we'll be crossing out a 0 over 0? Are we actually letting h get to 0? Just approach 0, so that's fine. We can do that. And this is your process for finding the slope of the curve to point. What you ultimately want to do, you want to cross out this h. That's pretty much your goal. That's it. As soon as you get rid of that, you'll be fine. Plug in the number. So here we have h, 2 plus h over h. Are you okay on the factorization? Can we cross our h's out? Notice how we don't need to get rid of all our h's, right? Just the one that's causing us the problem. Just that one. Notice how I'm still writing the limit. Anytime you have an h, you're going to write the limit. Now, am I okay to evaluate this limit as h goes to 0? Yeah. Now we're fine. We have no issues. Now you stop writing the limit. You write 2 plus 0. 2 plus 0 is, of course, 2. Okay, that's kind of cool. What's the slope of that curve at the point 1, 1? 2. You just found it. You found the slope of that curve at that point. And now it made a whole lot more sense because we got to use limits with it. So the slope of that tangent line is 2. Can you find the equation to the line? What do you need to find the equation for the line? You need two things always to find the equation of a line. Point and slope. Do we have a point? What's the point? Okay. Do we have a slope?
2.
We do now because we just. use limits to find one. That's kind of neat. And we'd use the slope, now the point slope formula, y minus y1 m x minus x1. Why don't you plug that in there and see what you get, okay? You can all do that. What you've just found on your paper, if you did that by yourself, what you just found on your paper is the slope of a tangent line to the curve x squared at a point. That's the only tangent line that's going to exist at that point. Now here's my question. Is the tangent line going to be different for a different point? For instance, if I give you the point 2, 4, are you going to have a different slope? It's a parabola, right? Yeah, it has a different slope at every single point. Every point has a different slope. So yeah, it's going to be different. You have to redo this every single time. Ultimately, I'm going to give you a way so that you can find the equation for the slope of a tangent line. That's going to be a little bit better. So we'll do that at the end. I just wanted to get you this picture in your head because I've actually given you this example before. Do you remember it? I did that example for you. I did it a long way though. It was a ways back. But now we have a better way using limits, and we didn't have to make that jump. We didn't have to make the limit jump because now we define limits so we can actually use that. Let's go ahead and start one more. I want to get the first couple pieces of this down, and then we'll continue next time. So next up, isn't that neat though? You found the slope of a curve at a point. I think that's so cool. That's why I love this class. You're able to do some neat stuff. Let's find the equation of the tangent line to this curve. At the point, well, let's see, 3, 1. I want to make sure the idea sticks in your head. So, firstly, what are we doing? What are you trying to find? Slope of the tangent line to this curve at that specific point. So we are going to be using that formula again. What I want you to do, see if you can find the two pieces that I need first.
Okay, so f of x sub 0, well, x sub 0 first of all is 3. F of 3 is 1. Or I'll just keep it like that. F of sub 0 plus h. F of, or wait, 3 over 1 plus h. So we got 3 over 1 plus h minus 1 over h. Wait. 3 over 1 plus h minus 1 plus h, 1 plus h, 2 plus h, over 1 plus h over h, two plus h over h plus h squared. 3. This would be 3 plus h, wouldn't it? H over 3 plus h h over 3h plus h squared. Yeah. h3 plus h cancel out. Zero over 3 plus h.
How about f of x sub 0 plus h? In this case, can you tell me what is x sub 0, please? Is it the 3 or the 1?
3.
It's a 3. It's the x value. So x sub 0 is 3. So instead of x sub 0 plus h, we're going to be finding f of what plus h?
3 plus h.
So 3 plus h, right? It's one thing. Find f of 3 plus h. So I want that. I know that, oops, sorry. I'll write up here. X sub 0 equals 3. F of x equals 3 over x. That's always our first step. Find x sub 0 and find your f of x. But now what I'd like you to do in the last few seconds here, find f of 3 plus h, find f of 3. That will take care of your x sub 0 plus h and your f of x sub 0. Did you already find that as I was talking? Firstly, are you okay that x sub 0 is in fact 3?
Yeah.
Yes or no? Are you okay that f of x is 3 over x? So we have those two things set in stone. If you want to find, let's do the easy one first. F of 3, that just means plug in 3. You should get that value again if it gives you a point, because that is the output for that number. So we should get 3 over 3, or simply 1. Did you all get 1? Okay, that's the easy one. Now, the other one. F of 3 plus h. Is it going to be 3 over, well, what is it going to be? Are you going to have an h at the end or within the function? Yeah, it's 3 plus h, right? Non-separable. So this is 3 over what? That's exactly right. How many people have exactly that? Good for you. Okay, I'll show you what to do with that next time. We'll actually find the slope of that curve at that point. All right, so let's continue this problem.
Okay. Watch. Probably the rest of this tomorrow. Yeah. And then maybe a little bit of introduction to derivatives. And this one's only 6 minutes long.